When designing spacecraft structures, we must take into account their design loads when we're sizing the structure. There are two main types of design loads that must be taken into account. They are both loads during launch, as that is when the largest loads occur. The two load types are dynamic loads and quasi-static loads. These loads primarily act in two directions: in launch direction, also known as axial direction, and in lateral direction, i.e. perpendicular to the launch direction. To size a primary spacecraft structure, a two-step procedure must be followed, which I'll explain. The first step is to ensure that the lowest natural frequency of the spacecraft, a satellite for instance, is larger than the minimum required natural frequency of the launcher. Limiting the natural frequency this way in both the axial and lateral direction is necessary to avoid the occurrence of resonance between the launch vehicle and the spacecraft. A second advantage is that having a low dynamic coupling also results in lower loads acting on the spacecraft. So how do we find out about these frequency requirements? These requirements are dictated by the launcher. When you design a spacecraft for launch into space, there are a number of launch vehicles and launch locations you can choose from. Which one you select depends on your mission requirements, your budget, and often your country's geopolitical position. Once you've selected a launcher, its user guide dictates all the requirements your spacecraft has to meet before you're allowed to bring your spacecraft on board your chosen launch vehicle. One of the requirements specified are the natural frequencies in axial and lateral direction. For example, the minimum natural frequency of the Ariane 4 launcher is 31 Hz in launch direction and 10 Hz in lateral direction. For the space shuttle, they each are 13 Hz, for instance. The natural frequency of an object with mass m can be defined as 1 over 2 pi times the square root of the stiffness k over the mass m, with the stiffness k equal to load over deflection. So how can we apply this formula to our spacecraft? Many satellites can simply be modeled as a concentrated mass at the end of a clamped beam. M is the mass of your payload of your spacecraft and L the height of the spacecraft. The beam in practice is often a thin-walled cylinder whose mass is much less than the payload on top, which is why the mass of the cylinder, or bus as it is known, is neglected. The beam, like all beams, will have a stiffness EI and a cross-section A. We can now define a simple single degree of freedom system involving a mass m and a spring. We define one system in axial direction and one in lateral direction, each with their corresponding stiffness Kx and Ky. If we now look at an axially loaded beam, we know that the spring stiffness K of such a beam is equal to the modulus of elasticity times the cross-sectional area over the length of the beam. Similarly, for a laterally loaded beam, its lateral or bending stiffness is defined as 3 times the bending stiffness EI over the length of the beam cubed, in which E is the modulus of elasticity and I the principal moment for inertia or for bending. This moment of inertia can be seen as the resistance of the geometry or the cross-section against deformation. If we now substitute the expressions found for the axial and lateral stiffness into the formula for the natural frequency, we find two design requirements. In axial load, the stiffness Kx must be larger or equal to, open bracket, 2 pi times Fn close bracket squared times the mass m. And for lateral direction, the lateral stiffness must be larger than, open bracket, 2 times Fn close bracket squared times the mass m. This allows us to size our spacecraft in terms of length, width and thickness. Now, step 2 in sizing our spacecraft. We must also ensure that the spacecraft can withstand the quasi-static loads. These are the maximum stress at the clamp and the buckling load. Let's have a closer look at each requirement. Based on the minimum natural frequency, determine values for the cross-section A and the moment of inertia I. Then select a material with modulus of elasticity E. Using the basic stress formula and the given minimum axial and lateral static loads, Gx and Gy, determine the total stress. In order for the design to meet the maximum stress requirement, the stress found must be lower than the allowable stress. The allowable stress is defined as the ultimate stress divided by safety factor n. This safety factor depends on the type of verification and the launch organization or industry. The second criteria that must be met is the buckling load. Again, based on the minimum natural frequencies, determine values for A and I and then select a material. Using the Euler buckling criterion, determine whether the launch load in axial direction, Gx times the weight of the spacecraft, is smaller than the specified buckling load of the structure you designed. If your design meets all these requirements, it is one step closer to being launched.